Good morning, everyone. I am Zhimin Hu from Peking University. My presentation is Gaze Analysis and Prediction in Virtual Reality. This is my presentation outline. I will introduce my research background, related work, two of my publications, namely the SGaze paper and DGaze paper, conclusion and discussion. Recently, eye tracking technology has gained importance in many different fields. It can be applied to marketing strategy analysis, cognitive research, medical education, gaze-based interaction, collaborative system, and gaze contingent eyeglasses. In the field of virtual reality, eye tracking technology can be applied to gaze contingent rendering, redirected working, and gaze behavior analysis. However, currently, the most common solution for eye tracking in VR is a hardware-based solution which requires a device called an eye tracker. Eye tracker is accurate but is currently expensive, not widely available, and may need calibration, cannot predict future gaze position. Considering the limitations of eye trackers, we desire to propose a software-based eye tracking solution in VR that only employs information from the VR system. It means that we do not utilize eye trackers. Specifically, our goals are analyze users' gaze behaviors in virtual reality and predict users' gaze positions based on the characteristics of users' gaze. Our research is related to salient object detection. Salient object detection aims at detecting salient objects from images. Another important work is salience prediction. Salience prediction predicts the salience maps of original images. Compared with previous work, we desire to predict 2D gaze positions rather than detect salient objects or predict salience maps. Furthermore, we focus on 3D virtual scenes rather than images or videos. This is my first research. In this research, we propose a data-driven eye-hand coordination model called SGaze to predict gaze positions in static virtual scenes. This is the SGaze model. SGaze predicts gaze positions by considering users' head movements, their VR content, and their task. Specifically, we consider the eye-head linear correlation and the eye-head latence to predict gaze position. This video shows the prediction results of SGaze model. The green cross refers to the ground truth, the red refers to our method, and the blue is the baseline. We can find that our model performs better than the baseline. In my second research, I propose a salient-based gaze prediction model called DGaze to predict gaze positions in dynamic scenes. This is the architecture of DGaze model. DGaze consists of three modules: the salience encoder module, sequence encoder module, and gaze prediction module. The salience encoder module utilizes SAM ResNet to extract salience features from the VR content and then encode the salience features. The sequence encoder module employs a 1D layer to encode the object position sequence and the head velocity sequence. The gaze prediction module combines the outputs of the settings encoder module and the sequence encoder module to predict users' gaze positions. By setting gaze positions at different time intervals as our targets, this model can be trained to predict not only real-time gaze positions but also gaze positions in the future. Generally, DGaze is proposed to predict gaze positions without the help of any eye trackers. If an eye tracker is available, we can also encode the eye tracking data, namely the gaze position sequence, in the sequence encoder module to predict gaze positions in the future with higher precision. In this time, we call our model DGaze_ET, which means eye tracking data is also utilized. This video shows DGaze prediction results. The green cross refers to ground truth, the red is DGaze, and the blue is other method. We can say that DGaze shows higher accuracy than other method. So to conclude, we propose an eye-hand coordination gaze prediction model that can be utilized to predict real-time gaze positions in static virtual scenes. We also propose a CNN-based gaze prediction model to predict real-time and future gaze positions in dynamic virtual scenes. Finally, I have some key questions to discuss here. In my previous research, I only focus on free viewing situations. In the future, I want to extend my research to task-oriented conditions. What kind of VR task-oriented conditions deserve to be studied? VR games, 3D user interfaces, or other tasks? What factors may influence users' gaze behaviors in VR? Sound, body and hand gesture, behavior habit, or other factors. Finally, I'm also glad to discuss about potential application of eye tracking technology in VR. That's the end of my talk. Thank you.